Hey guys, as promised, I told you I'd make you a very quick video over the problem I gave you guys for homework, which was 2002B question 1 from the AP exam. This is a buffer problem, so let's just kind of go through and see if we can apply and work through the stuff we learned today in class, or at least learned on Friday in class. So if I'm going through and looking at this problem, the first thing I notice is that we have lactic acid, which we're given the equation up here, is monoprotic. All that means is it gives up one hydrogen, and that it dissociates in aqueous solutions. Of course, we've been doing this forever now. The one thing I will say is this is, I guess, a little bit of an older problem. In most cases, this would probably really have, let me see if it will let me type in here real quick, or if it's going to panic. There we go. It would have something more like that in it, where it would have the water written out and the hydronium. And of course that would be subscripted, but that's okay. You get the basic gist of it, which is all I'm worried about right now. So it would look something like that. From there, we're told that lactic acid has a 1.6% dissociation and a 50 molar lactic acid solution at 298 degrees Kelvin. Again, don't get too caught up on the temperature. This is just to recognize that it's 25 degrees Celsius, so all of our KWs and pH and POHs that we have been using still hold true, because remember, if temperature changes, KW changes, and that creates a whole slew of problems that we're not going into right this second. So let's go through and actually kind of work through this. The first thing is to write the expression for the acid dissociation constant, Ka, so it's just writing the Ka expression for lactic acid, and we're told to calculate its value. Okay, well, first things first, let's calculate Ka. Or not calculate, sorry, let's write out Ka. Ka is going to be products, so H3O, or hydrogen, depending on if you kept the water in there or not, C3H5O3 minus over our reactants, which is HC3H5O3, lactic acid. And yes, this is the same lactic acid that built up in your muscles after working out and can cause your muscles to cramp and all that fun nonsense. So same stuff. College Board likes to grab chemicals like that you are somewhat familiar with. So in terms of calculating the K value, let's work through that for just a second. It is going to require the ice table. Okay, I'm going to do it actually down here because I've got a little bit more room, and this problem will play off of that as well. So we have our reaction, which is just our lactic acid, going to hydronium because of the dissociation of the hydrogen, and the lactate ion. From there, we have our 0.50, don't care about water, 0 and 0. We're doing our ice table here. Okay, it's going to shift towards reactants, or sorry, it's going to shift towards products, my bad, because there's 0 over here, so our reactants are shifting towards our products. And we end up with this. Okay, so nothing new. The thing that is new is we're told, actually it's not new at all, it's stuff we've done before, but just not, I guess, recently per se, is the 1.6% dissociation. So let's just kind of backtrack and remind ourselves what percent dissociation means. It literally means the percent of our acid that dissociates into products. So in essence, what that means is that allows us to solve for X. So percent dissociation is how much dissociates, which is really just our X value, over the original acid, times 100 equals our percentage. So if we go through and plug that in, or solve it out, how much dissociates is our X value, because that's how much changes or dissociates from our acid. The amount of our acid is 0.50 times 100 equals our percentage of 1.66. And of course you can get rid of the 100 and call this 0.0016 if you want to, or 0.016, sorry. And you can solve it out from there. So it's kind of up to you how you want to do it, but that's your call. Okay, so what we get by multiplying basically across with the 0.5 over there, we get an X value is equal to 0.0, I forgot my decimal, 0.0083 molar. So that X value can now be plugged in for our X value all the way over. So we end up with 0.50 minus 0.0083, which of course is very small, 0.0083. I'm writing a 3, there we go. There we go. And 0.0083, which means now we can calculate our Ka value. Ka is going to be equal to concentration of hydronium, which is X, 0.0083, times the concentration of our lactate ion, 0.0083, all over 0.50 minus 0.0083, which is going to be essentially 0.5, but we'll go ahead and write up the number so we have the calculation, 0.4, whoops, sorry. I'm making this Friday afternoon 7th period, so I'm having a couple little snafus. I apologize. 0.4947. So now we basically go through and do the math. 0.0083 times 0.0083 divided by 0.4947. And we get a Ka value of 1.4 or 1.39 times 10 to the negative 4th. And in terms of sig figs, it is only 2 sig figs because of the 0.50. So I would do 1.4 times 10 to the negative 4th. Now, from there, it's asking us for pH for the second part. Well, the nice thing is we've already done all this magical work, and we remember that pH is affected by 2 species, hydronium and hydroxide. So our hydronium is here, and here is our concentration of hydronium in equilibrium. So we can find our pH. I'm just going to come up here in this little space, equals the negative log of 0.0083, which is going to be around 2. But let's actually get that. Negative log of 0.0083, we get 2.08. And remember with sig figs for pH, it starts after the decimal, so 2 sig figs after the decimal. Okay, so that's it for A and B. Done. Not too bad. All right, let's go down to part C. Part C, we're then told to calculate the pH of the solution when we take 0.045 moles of solid sodium lactate and add it to 250 milliliters of 0.50 molar lactic acid, assuming the volume change is negligible. So we have the sodium lactate and we have lactic acid. We need to start recognizing that when we see the conjugates, which are typically going to be associated with lithium or sodium or anything along those lines, that is the conjugate base of the acid. And anytime we have these 2 species put together, we're dealing with a buffer system, okay? So that's kind of the definition of the buffer, is the conjugate, which comes from the dissociation of the sodium lactate, and the acid, which is the acetic acid. So I'm going to stop here because I know these 2 problems are going to take a little bit longer than I have time in the video. It only lets me make up to 15 minutes. So I'm going to pause and start another video for you showing you how to solve for C and D. Thanks, guys.